Hello, this video will be a literature review on AI-driven data routing and load balancing in fog computing networks. Before we head into how AI have enhanced the reliability and efficiency of fog computing networks, what exactly is fog computing? Fog computing is a decentralized computing paradigm that is emerged as an extension to cloud computing through empowering the continuum between cloud and edge. The impacts of fog computing are not obvious, but that's only because if it is effective, it leads to improved network performance and scalability of many real-world applications we interact, such as smart cities and autonomous vehicle systems. As these smart devices are becoming an integral part of our daily routines, we can see a rising number of IoT devices, forecasted at 41.1 billion in 2030. Traditionally, the computational needs of these devices are handled by cloud computing, but with stricter latency and bandwidth requirements, there are concerns with real-time response, security, privacy, and financial scalability in the near future. As such, in this evolving landscape of distributed computing, the collaboration between cloud and edge through fog presents many benefits for applications. Architectures start to come up as fog solutions are developed. These motivations are the starting point to create these architectures, but for fog computing, a hybrid approach works best, as the network edge will be able to filter, preprocess, and aggregate edge data while leveraging the capabilities and flexibility of cloud services to perform complex computational tasks and data storage. There are many fog network architectures in academia, but within the context of this review, a simple three-tier hierarchical architecture will be sufficient for discussion. First proposed by Cisco Systems, this architecture is made up of a cloud layer, which stores servers and storage centers, a terminal layer, which contains all the IoT devices generating data, and a boundary layer, the focus of this review, with fog nodes that handle lightweight computational tasks, temporarily store said data, and support data routing and task offloading. Going into key technologies, software-defined networking and network function virtualization are enablers of data routing and load balancing. SDN is a network communication technology that separates network instructions from actual data. This separation allows centralized control and programmability of network resources, which is crucial for dynamic adjustment when changing network conditions. NFV complements SDN by virtualizing network functions and running them on fog nodes. Examples include gateways, switches, and firewalls. This allows for smooth management of computing, storage, and communication resources to meet evolving demands. When edge devices do not have the computational power to process incoming data and tasks, it will flow upstream to other fog nodes and ultimately to the cloud. But for every node that is passed, latency is increased, which degrades quality of service. Traffic routing solves this by deriving the optimal data transmission path in response to changing conditions. AI, specifically reinforcement learning techniques, have been highly effective in learning and adapting to dynamic network environments. Another area AI has helped is in load balancing. A vital problem in fog networks is the possibility of over or underutilization of resources when tasks are allocated. Load balancing ensures efficient dispersion of workloads across nodes to optimize performance, maximize resource utilization, and avoid computational bottlenecks. Studies based on real-world applications such as in healthcare and smart cities have showcased the effectiveness of load balancing algorithms that combine heuristic algorithms in AI techniques such as neural networks and Q-learning. The example shown here is my implementation of Dijkstra with a recurrent neural network to load balance incoming weighted tasks in a simplified network that have nodes that fail at random times. While AI offers a diverse array of tools to enhance data routing and load balancing, its implementation faces challenges in real-life scenarios. Fog devices need to communicate with each other for optimization, so there is extensive data sharing. Also, fog devices need to be deployed close to end users, which might be in places out of protection and surveillance. In terms of real-world adaptation, proposed AI models are usually tested in simulation environments and are black boxes, which lack transparency in real-world implementations. Finally, AI models expectedly use a lot of energy to run, which is not ideal in resource-constrained fog nodes. Fog computing is still in its early stages as a transformative approach to address these challenges. Federated learning for security, online machine learning for real-world adaptation, and energy-aware solutions are continued to be studied extensively. AI-driven methodologies have the potential to become the cornerstone of efficient fog computing networks, paving the way for broader adoption and real-world applicability. Thank you.